Welcome back to Honors Calculus. In this video, we're going to be talking about related rates. The idea here of related rates is where calculus really starts to come into its own. For anyone continuing onward in just about any path that really builds on calculus, this is the idea that you're going to be using. The derivative of a function is talking about the rate of change of that function, the change in y with respect to x, generally speaking. When we talk about how something is changing, though, in practical applications, we're almost always talking about changing with respect to time, not with respect to x. So we're going to change gears ever so slightly here. Instead of thinking about y as a function of x or f as a function of x, we're going to be looking at various parameters that are functions of time. And we're going to look at how those parameters change over time. Things like rate of speed, the change in how far you have gone with respect to time, or talking about acceleration, the rate of change in velocity over time. We'll be talking about draining a tank, so we're going to see a change in volume over time. We're going to talk about filling up a balloon, which will be an increase in volume over time. And when you think about filling up a balloon, you put more volume into the balloon, it causes the balloon to expand, which means that the radius is changing, the volume is changing, they're changing at different rates compared to each other. And let's dive in exactly with that example. Let me get my head out of the way, and I want you to consider a spherical balloon. Most balloons that I come across are not spherical, but spherical makes the math a lot easier, so let's just pretend and hope for the best. All right. So consider a spherical balloon. We're pumping air into the balloon. We'll say that the rate at which we're pumping air into the balloon is 4.5 cubic feet per minute. And I want to calculate how fast the radius of this balloon is increasing as the radius passes 2 feet. All right, so again, problem-solving strategies. You've learned these in the past. We haven't really talked about them in this course. But the four-step process of problem solving. Step one, make sure you understand the problem. Step two, come up with some sort of a plan. Step three, execute the plan. Step four, interpret your results and see what it means in terms of the system. So make sure we understand the problem. We're talking about a fairly large balloon. The radius of the balloon is 2 feet and we're still blowing it up. We're still inflating it further. So we're probably talking about a weather balloon or something like that. We're assuming that the balloon is a perfectly spherical shape. Again, most balloons are not perfectly spherical, but sometimes you will see things that as they get nearer their maximum capacity, they start to look more like a sphere and less like the teardrop shape that you most often associate with a balloon. Right. So the idea here is that the amount of volume change is constant. The volume is always increasing at the same rate. But as the balloon gets bigger, increasing the volume at the same rate is not going to cause the balloon to actually visibly grow any faster because the volume of the balloon compared to the change is going to be a changing ratio. So we want to see how that affects things, right? Conceptually, that's what we're looking at here. We are thinking about the volume of the balloon as increasing at a constant rate, but the apparent size change of the balloon seems like it's slowing down because the balloon is so much bigger than the rate of change as we get nearer a full balloon. Right. So, what kinds of things do we know about this problem? We know we have a sphere. If you don't know the formula offhand, some geometry formulas are very worth having offhand at ready reference. The volume of a perfect sphere is given by 4/3 times pi times the radius cubed. The volume of this sphere is changing, so it is a function of time. The radius of this sphere is also changing, so it is also a function of time. All right, some things that we also know. We know that air is being pumped into the balloon at a rate of 4.5 cubic feet per minute. Well, that tells us a lot of information about the units. That tells us that we're talking about lengths in feet, volume in cubic feet, and time in minutes. What else do we have? All right, 4.5 cubic feet per minute. That's how fast air is being pumped in, and pumping air into the balloon is literally changing its volume. So the change in volume over time, that's dV dt is equal to 4.5 cubic feet per minute, but 4.5 as a number is good enough. And that's constant. That's for all values of t, it's not a function. We know that there is some t, I'm going to call it t naught. It's the time that we care about. And at the time we care about, the radius is 2 feet. We're asked how fast is the radius growing? How fast is the radius increasing? How fast is the balloon growing? All of those things mean the same thing. That is the derivative of r, dr dt, or just r prime of t, at the time we care about t naught. We don't know what that is. That's the thing we're trying to find. Right? So r prime, or if you prefer, dr dt. That's how we were talking about it before. Right, so we've got an equation that has v and has r. And notice that if we differentiate implicitly, the derivative of v of t is going to be 4/3 times pi, those are all just constants, times the derivative with respect to t of r of t, the whole thing cubed. The derivative with respect to t of v is going to be dv dt. 4/3 and pi are going to be constants. The derivative with respect to t of r cubed, right? The derivative of something cubed is 3 times that thing squared. But because it's r, it's a function of t, we have to use the chain rule and multiply that times r prime, or dr dt. And so we could take an equation that is well known, we can differentiate implicitly, and that gives us an equation that has all the parameters we need. We know what dv dt is. We know what r is. And we're asked to figure out what dr dt is. So plugging in all of those numbers. Notice here we've got some 3's that cancel each other out. That's convenient. Right? 4.5 is 4 times pi times 2 squared times dr dt. 4.5 looks like an approximate value. I'm not going to try to make everything exact in this problem. So I'm just going to grab my calculator and punch in 4 times pi times 2 squared, which is 16 times pi. But the important thing is my calculator tells me it's something in the ballpark of 50.3. And then from here, 4.5 divided by that ugly number comes out at something like 0.090. At this point, as we're pumping 4.5 cubic feet per minute of air into the balloon, the radius of the balloon is increasing at a rate of 0.090 feet per minute. Not exactly very fast. But that gives us everything we need. That's the basic idea here of related rate problems. Things can get to be a little bit messier when you have a couple of rates going on instead of just a single rate. So let's look at another problem. I want you to think about this trough, which is set up so that it is triangular sided. And we might know a couple of things about the trough. Say we know that this opening over here is 3 feet. The height of the trough is 5 feet. And the length of the trough is 12 feet. All right, so we know what the shape of the trough is. And we also know that the trough is currently filled with water to some level, not all the way to the top, but at some level. And let's say that we currently have a hose hooked up that is pouring water into the trough at a rate of 0.75 cubic feet per minute, which is actually the usual rate of the average garden hose. All right, so we are currently filling the trough. We know that the top of the trough is 5 feet tall. The top of the trough is open 3 feet wide. We are somewhere not full yet. Let's say that we are currently filled to a depth of 4 feet and we're still filling it up. All right, so currently the depth of this trough, or the water in the trough is 4 feet. And when the depth is 4 feet, we want to know how fast is the depth increasing? Or in more straightforward terms, how fast is the water level rising in the situation right at that moment? Right. Very similar to the problem that we were looking at before, but the geometry is such that the algebra is going to be a little bit more challenging. Once again, hopefully not difficult, but definitely more challenging. The first thing I want to do is remember the formula for the volume. The volume of a prism is the area of the base times the height. Very often you'll see that a triangle is given as area 1/2 base times height. Sometimes a little bit less often you'll see it as 1/2 times the altitude times the base. And the value of that is that we can talk about the height as being the distance in 3 dimensions, and we don't end up with overloaded units. All right, so our altitude is 5 feet, our base is 3 feet, and our height is 12 feet, and we are trying to calculate the volume at a particular time. Although again, because the water level is rising, we don't actually have those numbers exactly as we care about, because the volume is a function of time, the altitude is a function of time, the base is a function of time, the height is at least one thing that's constant. Right? As you are filling up this tube, or as you're filling up this trough, the water level, right? You have that V-shaped thing. As the water level rises, it's going to change the height. It's also going to spread out because it's further along the sides, not just going straight up and down. So the altitude, the depth of the water is going to change. The base, the width of the water at the surface level is going to change. The height, the distance across side to side on the trough, is going to be constant because those are straight rectangular sides. Right? That's the biggest trick of the problem, is understanding that bit of geometry. Once we have this, the rest of the process isn't that bad. I'm going to draw the side of the triangle really big and really poorly, but that's okay. All right. We know that we are looking at a particular point in time where the depth of the water is in fact only 4. And so in order to solve this problem, we are probably going to need to know how far across the water goes at that point in time. This alone is a challenging question. But notice that we have some similar triangles going on. The triangle on the outside and the triangle on the inside are going to be similar to each other because the angle in question here is the same. And unless something very strange has happened, the top of the trough and the water level should be parallel to each other. And so knowing that we have some similar triangles, we should be able to calculate using ratios. 3/5 equals our unknown b over 4. Which means that our unknown b at the time we care about is 12/5. So that's our b at the time t0 that we care about. All right, since h is not a function of time, I'm going to go ahead and plug in that value. 1/2 times 12 is 6. And at least setting that up gives me something that's a little bit easier to work with. But from here, I will differentiate implicitly. Derivative of v of t with respect to t is v prime of t. Derivative of a times b we're going to have to use the product rule. Derivative of the first times the second plus the first times the derivative of the second. And I should be using my colors a little bit more efficiently here. We solved for a particular time in our similar triangle over here. I could have just as easily solved it a little bit more generally, because that ratio, 3/5, should be equal to b of t over a of t at any time t. Which means that 3/5 of a of t is equal to b of t. I don't necessarily need that in general, although I can use that to my advantage. I can use that so that I don't need to have b of t naught as a separate thing. I can also use that to differentiate implicitly again. All right, differentiating this equation implicitly, 3/5 of a prime of t is equal to b prime of t. So if I plug in b of t and b prime of t with those results, I can simplify and only have the rate that I know and the rate that I care about, and get rid of the extra b prime of t that I know is changing, but the problem doesn't ask for and doesn't give me. All right, so 6 times 3 is 18. Notice we have a times a prime, 18/5, both times. 18 plus 18 is 36. And with that, we have what we need. We can start plugging stuff in. The rate at which water is entering the trough was 0.75. The depth that we cared about, A, at the time we cared about, was 4. And we had no idea what A prime was. From here, we could solve numerically if we wanted to, or analytically, we could get an exact value, but I'm just going to grab out my calculator. We've got 0.75. We need to multiply times 5. We need to divide by 36, and then we need to divide by 4. And all told, we get 0.026. (0.026 feet per minute. That's a little bit less than 1 inch per minute. All right, so I think that example gives a really good illustration that these related rates can be a little bit messy. It's a little bit difficult to see what's happening. To give you a better illustration of that, I would like you to try the same problem with something slightly different. So let me get my head back out of the way. Let me go ahead and copy this picture of the trough that we had before. And the thing that I'm going to change is, instead of thinking about what is happening when the depth of the water is 4 feet, I want you to look when the depth of the water is 2 feet. All right, so the same problem, the same setup, I've changed the depth of the water. Think about what, if anything, changes in our setup, calculate this, and then talk a little bit about how the rate at which the water level is increasing changes when the water is 2 feet deep compared to when the water is 4 feet deep. See what you can do with that, and I'll see you in the next video.